So in terms of refraction, we're actually going to look at a special case here. Now you may see the word reflection and think that's a typo. I assure you it's not. I will get to that. So we have a ray of light. It's got an angle of incidence of 64 degrees, and it's going to pass from water, index of refraction of 1.33, to air, index of refraction of 1. So let's find the angle of refraction. So once again, what do I know here? I know N1, my incident medium, is water. I know my refracted medium in this case is going to be air because I'm going from water to air. And then I know my angle of incidence is 64 degrees. So I'd like to find theta 2. Let's have a look at what's going on here. So we know that sine of theta 2 over sine of theta 1 is equal to N1 over N2. So sine of theta 2 is going to be N1 divided by N2 times sine of theta 1. All right, so let's calculate this. So we know N1 is 1.33. We have sine of 64 degrees. And then we're going to divide that by 1. So then what we're going to get is we're going to get sine of theta 2 is about 1.1954. Now for my really advanced math students, you're going to start to see there's going to be a little bit of an issue here. So sine of theta 2 is going to be that. Well, when I try to do theta 2 sine inverse of that, I'm going to get an error in my calculator. As you know, sine of an angle can only take values between -1 and +1. So if it's outside that range, we can't do much with it. So we can't actually calculate a value for the for the angle of refraction. And now you might have your faith shaken in Snell's law. You might say, did I just teach you something that was invalid? No. But you have to remember a few videos ago, I said when we're going from a high index to a low index, the angle increases, but I put a star next to it because I said that that's not quite the end of the story. Here's the other half of it. So when we're going from a medium of high index of refraction to low index of refraction, there can be the case where there is no actual refraction. So for that, if you look at this diagram here, so we have a light source, we have varying angles of incidence. So you notice I start to increase the angle. So at 0, it's just going to go straight through. Then 20, angle of incidence of 20, we have an angle of refraction 27 degrees. So as we keep increasing that angle of incidence, you're going to start to notice that angle of refraction increases. But at 50 degrees, we notice that there's no actual refracted ray. We actually have the light remaining inside the medium. So this concept of where there is no refraction, all of the light remains in the original medium where it's reflected in, this is what we refer to as total internal reflection, or sometimes for shorthand TIR. Now TIR is a special case and it only applies when we're going from a high index medium to a low index medium. You will not have TIR when you're going from low to high. So what's actually happening here is as we increase that angle, we're increasing that angle of refraction, but eventually we're going to kind of get to a special angle. And let me sketch this on the following page. So what's actually going to happen is eventually we're going to get to this special angle where I'm going to have this angle of incidence such that the refracted ray is going to run parallel with the boundary, or we'd say that the angle of refraction is 90 degrees. So this angle is really special. This is what we actually call the critical angle. So the critical angle is basically up to that angle, refraction is still going to occur. Once we exceed that angle, we will no longer have refraction. It will not be possible. After we hit the critical angle and go beyond that, all of that light, once it hits the boundary, it's going to all be reflected back in that medium. So that once we exceed theta c, or that critical angle, we will have this concept of total internal reflection. So a lot of times when you're asked to solve questions like this, you'll probably be asked to find the critical angle. So for these type of questions, main thing, you don't have to do this first part. We can set the angle of incidence, we can call it theta c, the critical angle. That's not actually important. The main thing, and we won't tell you this, when you're finding the critical angle, you're trying to find when that refracted ray of light kind of skims that boundary here, or that it's 90 degrees relative to the normal. because you want that ray of light to travel along the interface. So let's look at a question with this. So we want to find the critical angle for the water-air interface. The index of refraction of water is 1.33. So for the critical angle and for total internal reflection to occur, we have to be going from water to air, because we have to go from high to low index. So we must go from water to air, which is telling us that N1 is going to be our 1.33, N2 is going to be our 1.00, theta 1 is going to be the critical angle we want to find, and then for total internal reflection we want theta 2 to be 90 degrees. So we would like to find theta 1. So we know that sine of theta 1 over sine of theta 2, this is going to be N2 over N1, where sine of theta 1 is N2 over N1 times sine of theta 2. So let's plug in what we know. We know N2 is just going to be 1.00, we know N1 is 1.33, and then we have sine of 90 degrees, which you know is just going to be 1. So what we're going to get here is that sine of theta 2 is going to be about 0.7519. Now I don't want sine of theta 2, I would like the inverse sine of this. So what I'm going to get here is I'm going to get my angle is about 48.8 degrees. Now let's put this number into context for a minute. Basically what this is saying is that when the angle is up to 48.8 degrees, we will still have refraction. At 48.8 degrees, we are going to have that refracted ray skim along the boundaries. Once we exceed 48.8 degrees, there will be no refraction anymore. It'll just be complete total internal reflection. So I'm going to mark that on the side here. So just like, so this is kind of like a for your information. So when the angle is less than 48.8 degrees, we're going to have refraction. So refraction occurs. So when theta is equal to that 48 point, this is the critical angle. So the refracted ray is along the boundary. And then of course, once we exceed that 48.8 degrees, there is no refraction at this point. So this is just going to be total internal reflection. But yeah, on a diploma, it's usually very common to ask you about like critical angles and finding the index of refraction, or something of that sort. Usually you're trying to relate the two, but the main thing is that when you're dealing with total internal reflection, set theta 2 equals to 90 degrees, because you're usually trying to find that critical angle. And when we're talking about total internal reflection, probably one of the biggest applications of it has to deal with fiber optic cables. So you'll see this core of a fiber optic cable and it's surrounded with cladding. So the first thing is we want the index of refraction of the core to be greater than the cladding. And what we generally want to do when we send that signal in is we want to send that signal in such that its angle is greater than the critical angle, such that the signal is always reflecting inside the core. So we don't want any of it refracting out. We'd like to maintain that signal inside the core. Now, eventually there's going to be some signal leakage, so it will have to be reamplified. But the goal is, for a fiber optic cable, we always want that continuous total internal reflection so that the signal stays inside the cable and we don't experience a lot of losses. But yeah, this is probably one of the biggest like real world applications of total internal reflection.